Welcome, this is Dr. Amanda Rockinson-Zapcu. In this presentation, we are going to focus on bivariate zero-order correlations. During our time together, we are going to briefly look at research design and different correlational analyses. We're then going to define the bivariate zero-order correlation. We're going to look at examples of when this correlation analysis is used, look at the different terminologies, and really discuss in depth calculating Pearson's R. We're going to talk about assumption tests needed for bivariate zero-order correlations. We're also going to talk about hypothesis testing, the actual analysis, and then we'll take a look at an APA results section for a bivariate zero-order correlation, specifically the Pearson's R moment correlation coefficient. And finally, we'll look at how to set up an SPSS data set for this analysis. Let's go ahead and get started. Before we take an in-depth look at bivariate zero-order correlations, we're going to talk a little bit about research because it's important to understand where and when to do a correlational analysis. Most researchers conduct research in 1 to 2 categories, and that's either correlational or experimental. And our focus, as you've probably already guessed, is correlational research here. In correlational research, we do not attempt, or at least we try not to influence any variables, because the intent is simply to measure the variables and then look at the relationships between them, or the correlation or association between them. Whereas in experimental research, we manipulate some variable and then we measure the effect of that manipulation on another variable. Oftentimes we designate one variable as the dependent variable or response variable, and the other variable as the explanatory or independent variable. Explanatory or independent variables are potential causes or influences on the response variable. However, oftentimes a researcher simply wants to know if a relationship between variables exists. They really don't want to categorize the variables as a response, an explanatory, or an independent and dependent variable. There are situations where they don't want to explore the cause and effect relationships, and therefore they just focus on variables of interest or criterion and predictor variables. This is the case when a researcher desires to do a simple linear correlation and regression or a multiple linear correlation and regression. And these are really statistical methods for modeling the relationship between 2 or more random variables. There's simple linear regression, and that refers to a regression on 2 variables, while the multiple regression refers to a regression on more than 2 variables. A linear regression assumes the best estimate of the response in a linear function of some parameters. There are then correlations, and there are 3 specific what would be considered simple linear correlations. And these include the zero-order correlation, the partial correlation, and the part correlation. Let's go ahead and define these further, and then we'll take a really in-depth look at the bivariate zero-order correlation. The part, or semi-partial correlation, examines the relationship between 2 variables after removing a third variable from just one of the variables. This is sometimes used, but more often when a researcher is conducting a bivariate correlation or wants to do a simple correlation, they'll conduct a partial correlation. And a partial correlation examines the relationship between 2 variables after removing the overlap of a third or fourth or fifth variable, and it removes it completely from both variables. However, in this tutorial, we are going to focus on the zero-order correlation. And the zero-order correlation is probably the simplest of all correlation analysis. And this correlation simply examines the relationship between 2 variables while ignoring the influence of all the other variables. We're specifically going to take an in-depth look in this tutorial at the Pearson's product moment coefficient. As we move on to discuss the bivariate zero-order correlation, and more specifically the Pearson's product moment coefficient, it's important to understand the purpose of correlation research and correlational analysis. It's a common error to confuse correlation and causation. Correlation is necessary, but it's not sufficient. It's not a sufficient condition for determining causality. Correlation describes simply the relationship between two variables, but it does not explain why the variables are related. You cannot determine a cause and effect relationship when using correlation studies or a correlational analysis. When you're doing it, or when you're conducting a correlational analysis, it's really important that you never use the term cause and effect. You simply use the term relationship. And this is because all that correlations show us is that the two variables are associated or related, and there may be a third variable, a confounding variable that's related to both of them. Let me give you an example. Monthly deaths by drowning and monthly sales of ice cream are positively related or associated. But no one would say the relationship is causal. Why? Think about this for a moment. There's a relationship between drowning and monthly ice cream sales. Does that mean that if I eat ice cream that I'm more likely to drown? No, probably not. And you've probably at this point identified why that is. A confounding variable that actually explains the relationship is temperature. So it's important as we talk about correlational analyses that you remember that association does not imply causation, at least the way that it appears to on the surface. Okay, now let's get started talking about the bivariate zero-order correlation analysis. Let's start by making sure we understand when it's used. A researcher uses a bivariate zero-order correlation analysis when the researcher wants to examine the relationship or association between scores on two variables. More specifically, a bivariate correlation assists the researcher in examining the strength and the direction of the linear relationship between two variables, often referred to as x and y. There are two types of coefficients that are often used. First of all, there's the Pearson's product moment coefficient, and this is used when the researcher has two continuous variables, that is, variables measured at either the interval or ratio level, or one continuous and one dichotomous variable. Now, the Pearson's product coefficient ranges in scores from +1 to a -1. A plus indicates a positive relationship between the variables, whereas a negative sign indicates a negative relationship between the two variables. The value indicates the strength of the relationship. So, for example, 0 indicates no relationship, and +1 or -1 indicates a strong relationship, often referred to as a perfect correlation. This is important to just keep in mind right now. However, we are going to discuss this in depth in a few minutes. The other coefficient that's often used is the Spearman rank order correlation, or Spearman row, as you might have heard it called. This is used whenever data is ordinal, or the data doesn't meet some criteria. One of the assumptions for a Pearson's product moment coefficient is violated. So this is a good non-parametric alternative. There are others that we'll talk about again a little later, but it's important that you recognize these terms. For the purpose of this tutorial, our primary focus, as I've already mentioned, is going to be the Pearson product moment coefficient. So, to review, for a Pearson's product moment coefficient, or a Pearson's R, the researcher needs to have two variables, either two continuous variables, that's variables measured on the interval or ratio level, or one continuous variable and one dichotomous variable. Let's look at an example of when a researcher may use a Pearson's R. In conducting a literature review on sense of community, a researcher finds literature that suggests that a relationship exists between sense of community and perceived learning among graduate-level students enrolled in online educational courses at a U.S. university. Now, the researcher desires to build upon this research and further test the theory of social constructivism and some of the community models that have been set forth for online education. Thus, he proposes the following question: is there a statistically significant relationship between online students' sense of community and, instead of their perceived learning, their course grades? Now, since the researcher simply wants to look at the relationship between two variables measured at the interval or ratio level, a bivariate correlation is appropriate, and more specifically, a Pearson's R is appropriate. Now, the hypotheses for a bivariate correlation or a Pearson's R are as follows. First of all, the alternative hypothesis says that there is a statistically significant relationship between X and Y. In other words, R does not equal 0. The null hypothesis alternatively states that there is no statistically significant relationship between X and Y, and that R is equal to 0. So stated in terms or in alignment with the research question, in word format, the alternative or research hypothesis is that there is a statistically significant relationship between online students' sense of community scores and their course grades. And the null hypothesis, which will be tested in the analysis, is that there's no statistically significant relationship between the online students' sense of community scores and their course grades. In this example, the researcher would collect pairs of scores for each participant to see if the scores are related to each other in a specific way when all the scores of the participants are taken into account. Here you can see an example SPSS file. You'll see that the researcher collected data on 5 participants. First, each participant has a score on the sense of community assessment, and then the final course grade is listed. Again, because the researcher wants to look at the relationship between these two variables and both are measured on an interval or ratio level, a Pearson's R is the most appropriate analysis to conduct. When conducting any correlation analysis, and specifically a Pearson's R correlation, one of the best ways to visualize the relationship between two variables is to make a scatter diagram or a scatter plot. A scatter plot shows the relationship between the two continuous variables measured on the same participant. The value on one variable appears on one axis, while the value of the other variable appears on the other axis. A point on the scatter plot represents the value of each variable for one particular participant or individual. In other words, you make 1 point on the graph for each pair of scores. One variable is listed on the x-axis here, and the other is listed on the y-axis. Note, if you have an experiment in which you've declared a response variable, an explanatory variable, or an independent and dependent variable, you always plot the response on the y vertical axis and the independent variable x on the horizontal axis. So that's just an aside in this case. So let's, now that I've explained this in words, let's go ahead and make it practical using our research example, which we've been discussing. Here you'll see the first dot on the left is from participant 5. Participant 5 has a score of 20 on the community scale and a score of 700 in the course. The next dot over and up, you'll see, is from participant 3. This participant has a score of 20 on the community scale and a score of 800 in the course. And so the points, you'll see there are 5 dots here representing the 5 participants that we saw the data for in the previous slide. You will have noticed that there is a visual trend in the pattern of dots in this scatter diagram or scatter plot. Most of the pairs of scores tended to increase together. That is, when the score on the community scale was high, the score on the course points tended to be high as well, and vice versa. We could say that the general trend was for the low scores to go with the low scores and the high scores to go with the high scores. This is an example of a pattern that represents a certain relationship between these two variables. However, before we start discussing what kind of pattern we're seeing here, we need to define some terms used in correlational studies so that we can better discuss these patterns. So let's go ahead and take a look at a few important terms. We are first going to discuss the form and the direction of the relationships that can occur between the variables. There are linear relationships, curvilinear relationships, and no correlation at all. We're first going to discuss the linear relationship. There are two types of linear relationships or linear patterns that can occur, or two directions the relationship between the variables can go. First, there's a positive linear correlation, which means that the two variables tend to move in the same direction together. This occurs when high scores on one variable go with high scores on another variable, and when low scores on one variable go with low scores on the other variable. A positive linear correlation will show a trend on a scatter plot with a line moving from the bottom left to the top right of the graph. There are also negative linear correlations. A negative linear correlation means that the two variables tend to move in the opposite directions of each other. It exists when a high score on one variable tends to go with a low score on the other variable and vice versa. A negative linear correlation on a scatter plot will appear as a trend toward a line going from the top left to the bottom right of the graph. There are also curvilinear relationships, and this is sort of like what it sounds. A curvilinear relationship is a relationship on a scatter plot that approximates a curving line. A commonly used example of a curvilinear relationship is the relationship between age and healthcare. Now think about this. Those two things are related, but the relationship really doesn't follow a straight line. Why is that? Because we know that there are two populations that tend to use healthcare more. Young children and older people tend to use healthcare more than teenagers and young adults. So you're going to see a strong relationship between using healthcare in young children, or using healthcare and being young, and then also a strong relationship between healthcare and being older. Finally, there's also no correlation between the variables. That is that on a scatter plot, what you see is that dots are randomly everywhere. There's no relationship between the two variables. Now let's take this a step further and revisit the concept of correlation coefficient, and more specifically the correlation coefficient that's widely used that we're discussing primarily in this tutorial, the Pearson's product moment correlation coefficient, or Pearson's R. Now, Pearson's R measures both the strength and the direction of the relationship between the variables, but to this point we've only discussed the direction. And we're going to discuss the strength a little bit later. But let's talk about the correlation coefficient in terms of the direction. However, before we do this, I want you to keep in mind that Pearson's product moment coefficient ranges from a +1 to a -1. So it ranges from a +1 to a -1. When Pearson's R is equal to 0, that means that there is no correlation. There's no relationship between the variables. Now, if there's a positive linear correlation between the two variables, then Pearson's R will be greater than 0. So it will range from either 0 to +1. And then if there is a negative correlation between the two variables, Pearson's R will be less than 0. It'll range from 0 to -1. If the correlation is curvilinear, then Pearson's R is not a good statistic to use. In fact, what you may find is there's no statistically significant difference, or Pearson's R may be equal to 0 or to be very, very low. So oftentimes another measure called Spearman's rho, which I mentioned a little earlier, is the best statistic to use when analyzing curvilinear relationships. We'll talk about it in a moment, and if you remember that I mentioned earlier that whenever there is a violation of assumption, then a Spearman for a Pearson's R, then Spearman rho is oftentimes the best analysis to use. And one of the assumptions that we'll review of Pearson's R is that there's a linear relationship between variables. Now, before we move on and talk about what these values mean and the strength of the relationship, I think it's important to stop and talk about how to calculate Pearson's R. Understanding how to calculate a statistic can really clarify and help us better interpret it. It helps us understand the concept. Here you'll see the Pearson's R formula for the standard score version. Now, authors such as Warner suggest that this version of the formula for computation of a Pearson's R is really the easiest to understand conceptually. Let's talk a little bit about this formula and how it corresponds to the following operations. First of all, each X and Y score is converted to a standard score or a Z-score. And then for each participant, for example, ZX is multiplied by ZY. And these products are summed across all participants. And then finally, this sum is divided by the number of participants. And this results in the value of R and falls within the range of -1 to +1. Now, this is only one formula. There are several formulas. For this specific formula, I would refer you to Warner so that you can see how she goes through and uses a data set to compute Pearson's R using this formula. In this tutorial, we're going to look at another formula and walk through it step by step for calculating Pearson's R. So let's go ahead and do that now. Here you'll see a similar formula for calculating Pearson's R, and this is the one we're going to walk through step by step. We're going to use the data set on this slide to compute Pearson's R. You'll notice that we're still looking at a case that's similar to what we discussed earlier in our example. We're going to look at the relationship between community scores and course points. But here, course points range from 0 to 100. So let's go ahead and take a look at step 1. Step 1 in calculating Pearson's R is to set up the data. The best way to do this is to make a chart using the given data. Here you'll see that we have 3 columns: participants, community scores, and course points. And that we would want to add 3 more columns: XY, X squared, and Y squared. After the chart is set up, we then want to fill in XY, X squared, and Y squared. So step 2, you multiply together X and Y together, and you fill in the XY column. And you can see this is already done, but for example, in row 1, 43 times 99 is 4,257. For participant 2, 21 times 65 is 1,365. Once the XY columns for every participant are completed, that you then want to take the square of the numbers in the X column and put the results in the X squared column. So here we can see that 43 times 43 is 1,849, and so on. So you fill in the X squared column for all of the participants. Step 4 is to fill in the final column. You take the square of the numbers in the Y column and you put them in the Y squared column. Here we see that 99 times 99 for participant 1 is 9,801. For participant 2, 65 times 65 is 4,225. Now we're going to move on to the next step in the next slide. Now, in step 5, we add up all the numbers in the columns and we put them in the results at the bottom. Here you'll see that the Greek letter sigma is a short way of saying the sum of. So we sum all the community scores and we get 247. If we sum all of the values in the XY column, we get 20,485. So here at the bottom of this table on this slide, you can see the sums. We use all of these sums and all of these numbers and place them into the formula to work out the correlation coefficient. So here you can see the formula that we're using, R equals, and if we plug in all the numbers here at the bottom, you'll see that once we calculate them all, we have a correlation coefficient of 0.5298 or 52.98%. So this means that the variable of community and course points have a moderate positive correlation. And we're going to talk about how I just used this number or this value to make the evaluation that we have a moderate positive correlation. However, before we move from this slide, I do want to make one note about the formula here. And it's because it's one number that we haven't talked about. N is important when calculating the correlation coefficient, and N you can see here equals 6, and I just wanted to bring that to your attention. And we have N equals 6 because we have 6 participants. So now let's go ahead and focus on talking about how we use the value to interpret the strength of the relationship between the variables of interest. So to this point, we talked about the direction of the relationship, and the direction is indicated by the sign. If Pearson's R is positive, it ranges between 0 and +1, then the correlation can be said to be a positive linear correlation, or the relationship between variables is positive. If Pearson's R is negative, that is, it ranges from 0 to -1, then it represents a negative linear correlation. However, the strength of the relationship is indicated by the number or the value. The values for the Pearson's R correlation coefficient, as you remember, range from +1 to -1 or -1 to +1. The strength of the correlation is indicated by, as I said, the number of Pearson's R regardless of the sign. So in other words, the absolute value of R tells us how strong a correlation or the relationship between variables is. According to Cohen's 1988 conventions, as we've already established, 0 indicates that there's no relationship. A 0.10 to 0.29 indicates that there's a small relationship between variables. 0.30 to 0.49 indicates that there's a medium relationship, and anything between 0.5 and 1 indicates that there is a large or strong relationship. Now, as we're talking about Cohen here, I want to take a moment and note that Cohen's conventions are used to interpret correlations coefficients in statistical reports. And it's good common practice every time that you use Cohen's conventions to interpret the relationship between variables or interpret the correlation coefficients that you cite the convention being used. Now, let's go back to discussing the strength of relationship. Understanding that the strength of a correlation is indicated by the number of Pearson's R, regardless the sign, is a little bit counterintuitive. So I want to take a few moments to spend some time talking about this. And it's more so counterintuitive because when you're looking at negative relationships. What I'm saying is pretty easy to grasp when you have a positive correlation, because a correlation of 0.67 is stronger than a correlation of 0.52. However, when the correlation is negative, it turns out that a correlation of 0.75 is stronger than a correlation of 0.25. And even more surprisingly, a correlation of negative 0.75 is also stronger than a correlation of positive 0.25. As I said, we're going to spend the next few slides and the next few moments talking about this more in depth, because this is a really important concept to understand. We are going to further discuss this concept of strength of relationship by examining this in the context of scatter plots. As you remember, to interpret a scatter plot, we look at the overall pattern. We can describe the overall pattern in terms of its shape, its direction, and its strength. Remember, in terms of direction, if the line around which the points tend to cluster runs from lower left to upper left, then the relationship between the two variables is positive. If the line around which the points tend to cluster runs from the upper left to the lower right, then the relationship between the two variables is negative. Now let's discuss the strength of relationship in terms of the scatter plot. The strength of the relationship can also be seen in how the dots or how the points cluster. If there exists a completely random scatter of points all over the place and they aren't really clustering in any way, there's probably no relationship between the variables. However, the more the points tend to cluster around a straight line in the scatter plot, the stronger the linear relationship between those two variables are. In other words, the higher the correlation is, the higher the value is. A strong correlation above a 0.5, whether it be positive or negative, is going to cluster around a straight line. So here we look back to the scatter plot from our example research. Here in our example, we see that the points on the scattered diagram are approximately a straight line from the bottom left to the top right. Therefore, we can say it's a positive relationship. And because here we can see that the dots go in somewhat of a straight line, we can also say that it is likely that the strength of the relationship is strong, that there's a large or strong relationship. Let's go ahead and look at a few more examples of this to further clarify it. In this scatter plot, you see almost a perfectly straight line of dots. A straight line represents a perfect relationship. In a perfect relationship, the value of R, of Pearson's R, is 1. So here you can see a scatter plot where the Pearson's R is equal to 1. In the middle on this slide, we see a gray scatter plot, or a grayish color scatter plot. And what we see here is there's a lot of random scatters of points. This scatter plot indicates that there's no relationship. And actually this scatter plot indicates that Pearson's R, or shows that Pearson's R is equal to 0. Now let's take a look at the pinkish colored scatter plot at the top right. We see that the points cluster around a straight line. And if you remember, this indicates that a strong linear relationship exists between the two variables because they're gathering around a straight line. Since the points cluster or run from the lower left to the upper right, we can then infer that the relationship between the variables in this data set is positive. And in fact, the Pearson's R for this data set is plus 0.70. Now let's look at the more beige colored scatter plot at the very bottom right. Here we see also, just like the one we just discussed, that the points of all the different points cluster around a straight line. This also indicates that there's a strong linear relationship between the variables. However, here we notice that the line around which the points tend to cluster run from the upper left to the lower right. And this indicates that the relationship is negative. However, for both the top and the bottom scatter plots, what we can note is that the relationship between variables for both of these data sets is strong. The strength of the relationship is strong at both a plus 0.70 and a negative 0.70. Now let's look at another set of scatter plots. As we noted that when R equals 0, meaning that there's no correlation, the dots are random, as we see again in the middle gray graphic. As we noted though earlier, as we move away from 0 in both directions, the correlation becomes stronger. That is, the relationship between the two variables becomes more obvious. And this is as the correlation coefficient approaches either a negative 1 or a positive 1. So 0.70 is stronger than 0.30 because 0.70 is closer to 1. In the same way, negative 0.70 is stronger than negative 0.30 because negative 0.70 is closer to negative 1. Here in the scatter plots, you can see that the dots in the bottom graphic illustrating a correlation coefficient of negative 0.70 are closer to 1 because they're more clustered around a straight line, whereas the top graphic illustrates that a correlation coefficient of negative 0.30, and you'll see that the dots in this scatter plot are not as clustered around a straight line. Now let's consider all of this information that we just talked about. Let's think about a question for a moment. Which correlation coefficient is stronger, a positive 0.32 or a negative 0.70? Here you'll see scatter plots for both of these Pearson's R. At the top you'll see the scatter plot when Pearson's R equals positive 0.32, and then at the very bottom you'll see a scatter plot when Pearson's R equals negative 0.70. Remember, when we're talking about strength of relationship, we're looking for our dots to gather around or cluster around a straight line. So which scatter plot demonstrates dots around more of a straight line? You probably said the bottom one, and that's right, because R equals 0.70 is actually stronger than a Pearson's R of positive 0.32. And this is because a negative 0.7 is much closer to 1, specifically negative 1, than a positive 0.32. Actually, the positive 0.32 is closer to 0 than the negative 0.70. So the 0.32 represents a weaker correlation, and a negative 0.7 or a 0.7 equals a stronger correlation. So when you're interpreting a correlation coefficient, especially in terms of strength, it's really important to remember that it can't be thought of as a number line, but it's an interpretation or judgment based on an absolute value or correlation. So negative 0.70, the 0.70 is larger, the relationship is stronger than the positive 0.32. So now we've talked about Pearson's R, we've talked about interpreting Pearson's R both in terms of strength and direction, and we've looked at scatter plots and are able to see strength and direction. We're going to continue our discussion about Pearson's R and zero order correlations. Since we're on the topic of scatter plots, it's important to recognize here that scatter plots are not just useful for examining direction and strength of a relationship, but they can also be very useful for examining assumptions. So in our next slide, we're going to talk a little bit about the assumptions for a Pearson's R. Here we see a list of assumptions that need to be met for the Pearson's product moment correlation coefficient to be robust. And as you'll notice in a few moments, many of these assumptions can be tested using the scatter plot. Let's talk about these in the order that they're listed. Let's first focus on normality. First of all, for normality, the distributions of both variables need to approximate a normal distribution. So you can check both sets of data. Let's say we were looking at the relationship between community and course points. We would look at the distribution of scores in community and the distribution of scores in course points. And we would check using either a histogram or some type of statistics such as the Smirnoff test or Shapiro-Wilks to determine if those distributions are normal. Here in this top graphic, let's say this was our distribution for community, we would say that the distribution is normal because it's what we see is a normal bell curve. Now, in addition to this, both variables should also have an underlying distribution that is bivariately normal, and this is checked using the scatter plot. If you have a bivariate normal distribution, what you'll see is a symmetric elliptical pattern. And bivariate normality indicates that the scores on one variable are normally distributed for each value on the other variable and vice versa. So that covers normality. You're looking at normality in each distribution, and you're also looking at bivariate normality for a Pearson's R. Also, another assumption that you want to look for, another thing you want to look for is for each variable or each value of one variable, for each value of one variable, the variability of scores on the other variable is approximately the same. And this is an assumption called the assumption of homodysticity. Another way to describe this is that the variability in scores in both variables should simply be similar. You check for homodysticity using the scatter plot, and what you're hoping to see so that the assumption is tenable is a cigar shape. Here you'll see two graphics in the middle, and they're two scatter plots. On the left hand side, what you'll see is all the dots kind of make a cigar shape. And so if this was our distribution, what we could say is that the assumption of homodysticity was tenable. However, on the other side, you'll see a scatter plot with the word violated in it. And here what we notice is that the points are really clustered close together on one side of the scatter plot, and they sort of spread out on the other side of the scatter plot. This does not make a cigar shape, and here we would say that this assumption of homodysticity is not tenable. Now, failure to meet this assumption and normality, it generally only has a small effect on the validity of a Pearson's R, but this is only when your sample size is over 25. If you have under 25, then these may be a great concern. Violation of these assumptions may be a great concern, and a non-parametric alternative should probably be considered. Now, while we're talking about homodysticity, let me make a quick comment here on a related concept, and that is a restricted range of scores, because restricted range of scores on one or both variables can reduce the correlation and the validity of your study. Let me give you an extreme example here. Consider for a moment that you want to know what the relationship between high school GPA and college GPA is in a sample of students. However, when you take the sample, what happens is that every student has the same high school GPA. Since there's no variation whatsoever in the variable of high school GPA, you have a restricted range. You're not going to have any correlation. And in fact, in this scenario, the correlation would be 0, when in fact what we know is there's actually a correlation or relationship between those two variables. Another way to think about restricted range, maybe not such an extreme score, is when a sample is being studied and it's limited in some way. So let's say as a researcher, I want to know what the relationship between IQ and job performance is. But whenever I send my survey out, what happens is only college-educated individuals participate. So what's going to happen is most likely, since I have college-bound or college-educated individuals, is that maybe the IQ scores that I have are going to be range a little bit higher. And maybe even job performance would range a little bit higher. The range of scores is going to be restricted because of the specific types of individuals that participated, and thus that's going to affect the validity of my study. So that's just another note there. Let's go ahead and keep moving on through our different assumptions. The next assumption that's really important and can really affect the validity of a Pearson's R is no extreme outliers. No extreme outliers can be checked using a box plot. It can also be clearly seen, and you can see it here. It's the very last graphic using a scatter plot. What we see is that a bunch of scores are clustered here at the bottom, and then there's one that is way outside of the cluster, and that would indicate an extreme outlier. Outlier. Now, extreme outliers, even one single extreme outlier, extreme score, can truly confound a correlation. And let me give you an example. In this bottom picture that we've been looking at, we see a scatter plot with one extreme outlier. When that extreme outlier is included, and you calculate Pearson's R, what happens is that Pearson's R is a positive 0.53. Now, if I remove that outlier, what we find is that Pearson's R is then a 0.86. So you can see that extreme outliers can significantly influence the correlation found. Another important, and in fact one of the assumptions that I realized I just skipped right after normality is linear relationship. Remember I said earlier Pearson's R assumes that there's a linear relationship between the two variables. And if there's not a linear relationship, then a Pearson's R is not a robust test. Oftentimes what you'll see is that there's no correlation, and whenever there's not a linear relationship, most likely you have a curvier linear relationship. And remember, I said you can then use a Spearman row. There are two more assumptions listed here. The next is random sampling. The sample, ideally what would happen when you are looking at the relationship between two variables is that your sample represents your population. If your sample is going to represent your population, ideally your participants are selected using random sampling. Now, this isn't always possible in educational research, but it is ideal. But you can still use a Pearson's R if you don't have a random sample. You just need to note that as a limitation in your study. And finally, the variables that are used in a Pearson's R, specifically at least one of them, needs to be measured on an interval or ratio scale. Many researchers support the use of a Pearson's R2 with ordinal level variables that have several response levels. For example, Nolly and Bernstein in 1994 asserted that the Pearson's R can be used with ordinal variables. However, it's usually recommended, and they said I think it's 11, that if the ordinal variables, if there's more than 11 ranks, then it's probably okay to use a Pearson's R with ordinal data. However, a lot of statistical texts will say if you have ordinal data, the best choice is to go ahead and use a Spearman row. So if you have ordinal level data or nominal level data, and these violations in any way are these assumptions are violated in any way, then oftentimes it's better to use a non-parametric alternative. And so we're going to talk about a few of those next. So if any of the assumptions we just talked about are violated, here is a list of alternative correlation coefficients. Probably the most commonly used when assumptions are violated is Spearman row. Spearman row is a measure of the linear relationship between two variables. Again, it's a non-parametric test that uses rank. It's used whenever it can be used with any type of data except categorical data. So if you have ordinal data or like I said, some assumption is violated, then Spearman row may be a good alternative to Pearson's R. There's also Kindle's 2, B, and C. Spearman's row is not especially robust when it comes to really small sample sizes, particularly when there are a number of tiered ranks. So if your sample size is less than 10, Kindle's may be a good option. Now there's differences between B and C, and if you're looking at using these, consulting statistical text to learn about the difference and when to use them is important. Another is gamma, and sometimes you'll hear this referred to as Goodman and Kruskall's gamma. It's another measure of the relationship, and it, just like Pearson's R, varies from +1 to -1. And gamma assumes that both variables are ordinal, so that's one reason that you'd use it, because you have ordinal data. And while categorical interval data might also be used with this measure, information is lost in the categorization process, and a better assessment of strength of relationship is attained by using continuous data with an interval level measure such as Pearson's R. So if gamma is, let's say, 0.636, for example, we may say that knowing the independent variable reduces our errors in predicting the rank, not a value, of the dependent variable by 63.6%. Somers is another option. Gamma, Kendall's, and Spearman's are all symmetric, and consequently they really make no distinction between independent and dependent variables. And so Somers D is an asymmetric, and unlike all the correlation coefficients we've talked about to this point, it assumes that you can identify one variable as more the dependent variable. So if that's something you're interested in, this may be a good option. All of these alternatives require that you use ordinal data. They're not good for using, or they're not good when you want to examine categorical data. So if you have categorical data, or you want to look at nominal measures, some alternatives there are phi, Kramer's V, contingency coefficients, lambda, or the uncertainty coefficient. So if you're looking at categorical data, those may be some options. If you want more information on any of these, I highly recommend that you consult statistical text and read more in depth about these. But for the purpose here, I just wanted you to be aware of some of the alternatives you have to Pearson's R in case your assumptions are violated. So now we've talked about assumption testing and Pearson's R. In any analysis, you're going to start with doing assumption testing to determine if any of the assumptions have been violated and if the analysis is robust. After assumption testing, you usually, such as in the case of a t-test or an ANOVA, you usually do hypothesis testing by calculating a t-value or an f-value, and then you calculate the effect size. However, in a correlation analysis, as we've been talking about Pearson's R, what we need to note is that actually Pearson's R is the effect size. So we're talking about things a little bit backwards here, but it all makes sense in a moment. We've discussed Pearson's R, and so using Pearson's R, what you can note is that you can make statements about the strength and direction of a relationship between two different variables. That's what Pearson's R allows you to do. It allows you to determine the effect size. It's important to note that Pearson's R does not, however, tell you if a significant relationship exists between variables. This still is a decision that has to be made as a result of hypothesis testing, just like you would do whenever you conduct a t-test or an ANOVA. So, the first thing that really needs to be done before you can interpret Pearson's R and what it means is that you need to do hypothesis testing. Now, if we remember back to our example, research example, remember the null hypothesis states that there's no relationship between variables. To test this, we conduct a t-test. So let's talk a little bit about this and the steps that you take to conduct a t-test. Interestingly, the first thing you do is you calculate Pearson's R, which we've already talked about doing. So once you have Pearson's R, you can continue with calculating the t-value. Usually after you calculate your R, the next step you're going to take before you actually go ahead and calculate your sample's t-value is you're going to look up, remember, the critical t-value in a t-table, and this is found in most statistical texts, and you look up the t-value in the t-table based on the degrees of freedom. For a correlational analysis, degrees of freedom is n minus 2. After you have your critical t-value, you can then go ahead and calculate your sample t-value. This formula can be found in many statistical texts, but I've also included it here on the slide. What you'll note here about this formula is that there's only two ingredients needed, the sample n and the R value, and we'll discuss why this is significant in a moment. So we've talked about steps 1, 2, and 3. You calculate your R value, you look up your critical t-value, you calculate your sample's t-value. Now you can compare your sample's t-value to the critical t-value found in the t-table. And if the t-value is significant, this means that you can state that there is a significant relationship between the two variables, and you can go on to talk about the effect size, Pearson's R. What is the strength of this relationship? What is the direction of the relationship between these two variables? If t is not significant, this means that there's no statistically significant relationship between the variables, and when you're writing up a report or talking about it, you should not necessarily discuss Pearson's R at that point. You can just simply state that there's no statistically significant relationship. Now, in addition to using a t-value for hypothesis testing, Some authors also discuss an f-value. So an f-value can be calculated. I've included the formula here and used for hypothesis testing. Statistical texts such as Warner and Tabachnik and Fidel discuss this alternative formula in great detail and when to use it. It's not something that I'm necessarily going to discuss. I'm not going to discuss it here, but it's something you do need to be aware of. Now we've talked about hypothesis testing and hand calculating. What we know for the most part is that we're going to use statistical software to calculate both Pearson's R and the significance level. So let's take a moment here and talk about the SPSS output and what can be done with it. When using SPSS, any correlation test, including a Pearson's R, will calculate two values. It will calculate a p-value in addition to the correlation coefficient. For educational research, remember, or any social science research, if a p-value is greater than 0.05, there's insufficient evidence to reject the null hypothesis that there's no relationship between the variables. So if the output shows you a p-value of 0.06, what can be concluded is that you fail to reject the null hypothesis and state that there's no statistically significant relationship between the variables. However, if the p-value is less than 0.05, you can reject the null hypothesis, state that there is a statistically significant relationship between the variables, and then discuss the effect size or Pearson's R. Now, as I noted earlier, whenever the t-value is calculated, there's two ingredients, R and N. The statistical significance of a correlation coefficient is thus strongly affected by the sample size. In fact, almost any correlation coefficient can be found statistically significant if a sample size is large enough. So if you do find statistical significance, examining the strength of the relationship and interpreting the practical significance via that correlation coefficient becomes very, very important. So that's just something important to note. So now we've talked about assumption testing, hypothesis testing, and effect size. Let's move on and talk about reporting these results in APA format. When conducting and reporting the results of a correlation analysis, a Pearson's R, here's a list of the items that you need to report: the assumption testing, the descriptive statistics, the number of participants, the degrees of freedom, the significance level, the effect size, and the power. Here you can see the process for communicating your results via APA style, how to report the items we just reviewed. Remember, it's always important to state the statistical results of a correlation procedure, and here's an example of how those may be reported. R, in parentheses you see degrees of freedom, R equals 0.51, and the p-value equals 0.02. Now it's important to interpret those or discuss those results in sentence form. So here you can see an example. A zero-order correlation was used to evaluate the null hypothesis that there was no statistically significant difference between students' sense of community and their total course points. And this is similar to the example that we've been talking about throughout this tutorial. Here we can see that the N equals 20, which means there were 20 participants in this specific analysis. And what we can see is that the Pearson R analysis, what it yielded was that there was a strong positive correlation, a statistically significant strong positive correlation. And how do we come to that interpretation? Well, first of all, we're going to look at our p-value. Our p-value is less than 0.05, and since it's less than 0.05, we can say that our results are statistically significant. We can then interpret the R. Now, there's no negative sign in front of the R. There's a positive sign, so that tells us that the relationship between variables is positive. That means as sense of community increases, the total course points increase. And since it's 0.51, remember, based on Cohen's convention, anything above a 0.5 can be considered a strong correlation or strong relationship. Since our significance level is below a 0.05, we can say that we have evidence to reject the null hypothesis. These are all important things to communicate when you're reporting results of a correlation analysis in APA. I will state one reminder here. Remember, when you are interpreting Pearson's R, it's important to cite the convention that you're using. I know that's not done here in this example, but remember to cite any conventions that you use to make interpretations about your results. As we are discussing results and reporting results in APA, it's important to note that authors such as Warner and the APA manual suggest that reporting a single correlation is usually not sufficient for a dissertation, thesis, or publishable paper. So logically what you're thinking is well then just report a lot or a large number of correlation analyses. However, when significant tests are reported for a large number of correlations, there's an inflated risk of type 1 error. That is, there's an increased risk of finding significance in that set of correlations when there truly is not significance. So Warner suggests several ways that you can reduce this risk of inflated type 1 error. For example, she suggests that you report significant tests for a limited number of correlations. Your theoretical framework should drive the questions that you're asking and the hypothesis you are testing. So instead of looking at all the possible variables, limiting the number of correlations directly related to the theory that you're testing is one way to reduce the risk of inflated type 1 error. Warner also suggests using Bonferroni. She suggests using cross-validation within samples as well as replicating correlations analyses across new samples or a variety of samples. Thompson, in an article entitled A Primer on the Logic and Use of Canonical Correlation Analysis, suggests that perhaps instead of doing multiple bivariate correlations, multivariate correlation analyses should be considered. For example, when a researcher is seeking to understand the relationship between sets of variables, for example, let's consider the scenario that we have been looking at. Let's say that the researcher wants to know, is there a relationship between sense of community, and sense of community actually has two constructs, classroom community and learning community. And let's say that the researcher wants to know how those two community constructs relate to both perceived learning and actual course outcomes. So the researcher becomes interested in how multiple sets of variables relate. What Thompson says is that a canonical correlation analysis may be more appropriate as it limits the probability of committing a type 1 error. Remember, type 1 error, finding statistically significant results when it doesn't exist. Because what happens with a canonical correlation is instead of using separate statistical significance tests, this analysis can assess the multiple relationships between the sets of variables in a single relationship. So it considers all the multiple relationships among the variables. So a canonical correlation may be a more appropriate choice and may reduce the probability of committing a type 1 error if you as a researcher are looking at the relationship of multiple variables to multiple variables. If you're looking to determine the relationship between one variable and multiple variables, a multivariate analysis such as a multiple regression may be more appropriate for the same reason that Thompson says a canonical correlation may be more appropriate. Again, it's just limiting the number of multiple analyses. And so any way to limit the number of multiple analyses then decreases the risk of a type 1 error. So it's just important to note that number one, authors such as Warner as well as the APA manual suggest that doing one single correlation analysis is not sufficient for publication or for a thesis or for a dissertation, and that if you are going to pursue multiple correlation analyses, you may want to consider one of the procedures that Warner suggests for reducing type 1 error, or consider a multivariate analysis. But again, going in depth in this is not within the realm of this tutorial, but it is important to note as we are talking about reporting results. Finally, as we're ending our time together, I wanted to end this tutorial like I have the other ones, and show you an example of what an SPSS data file will look like when it's set up properly for a correlation analysis. This should look familiar, as we've already seen this when we were talking about our research example for a correlation analysis. Here you will see that each participant is listed, and each participant has 2 scores. These 2 scores represent the variables that we're going to examine in a bivariate correlation. Because remember, a bivariate correlation, specifically a Pearson's R, looks at the relationship between two different variables. This now concludes this tutorial. At this point, you should understand that there are various correlation analyses. You should understand the definition specifically for a bivariate zero-order correlation, and even more specifically for Pearson's R. You should be able to talk about examples of when Pearson's R should be used and when it should not be used. You should be able to talk about effect size and how Pearson's R can be used to interpret both the strength and direction of relationship between the 2 variables. You should be able to identify the assumption testing or the assumptions that need to be tested in order for Pearson's R to be robust. You should also be able to talk about hypothesis testing and be able to discuss the difference between Pearson's R and hypothesis testing, and how a significance level or a p-value is needed to determine the significance, and Pearson's R is simply the effect size that helps us understand the direction and the strength of the relationship. You should be able to identify the items needed to report a correlation coefficient, zero-order correlation in APA style, and finally how to set up a data set for a correlation analysis in SPSS.